Welcome to Brain Vision.
Our question is: an air standard cycle with constant specific heats is executed in a closed piston cylinder system and is composed of the following three processes. Isentropic compression with a compression ratio R is equals to V1 divided by V2 in the first process, 1 to 2. In the process 2 to 3, constant heat addition. In the process 3 to 1, constant heat volume rejection. In the part A, sketch the PU and T diagram, obtain expression for the back-work ratio. We have to obtain an expression for time cycles, thermal efficiency, determine the value of the back-work ratio and thermal efficiency as R goes to unity. What do your results imply about the net work done by the cycle? So, to solve the question, first we will sketch PV and TS diagrams. In part A, this is P and V diagram. One, two, and three. And this is the T and S diagram. Like this. Three, two, and one. So now in the part B, the work of compression is found by the first law in the process. The compression work of compression is found by first law for process 1 to 2. So Q 1 to 2 is equals to minus work done from 1 to 2 is equals to del U 1 to 2 in the process. And Q is equals to 0 in isentropic process. So our work done during the process 1, 2 is equals to minus U. That is equals to minus CV T2 minus T1. And work done during the compression is equals to minus work done is equals to CV into T2 minus T1. The expansion work is found by, this is the compression work, and now the expansion work is found by work done during the compression divided by work done during expansion, that is equals to CV T3 minus T1 divided by R into T3 minus T2. That is equals to CV T1. We take T1 common, and here R T2 common. In the process 1 to 2, isentropic is an isentropic process, therefore T1 divided by T2 is equals to V2 divided by V1 power K minus 1, which is equals to 1 over R power K minus 1, and P2 divided by P1 is equals to V1 divided by V2 power K equals to R power K. Therefore, during the process 2 to 3, there is constant pressure. Therefore, I'm writing it over here, P3V3 divided by T3 is equals to T2V2 divided by T2. From here, T3 is equals to T3 divided by T2 is equals to V3 divided by V2, that is V1 divided by V2, which is equals to R. So, during the next process, that is 3 to 1 constant volume. It's constant volume. Therefore, we will write P3V3 divided by T3 is equals to P1V1 divided by T1, which implies that T3 divided by T1 is equals to P3 divided by P1, which is P2 divided by P1 equals to R power K. So the back-work ratio becomes CV is equals to R divided by K minus 1. So our work done divided by compression into expansion is equals to 1 over K minus 1. Now we are putting the values. 1 over R power K minus 1 that we have calculated above, all are in the terms of R power K minus 1 divided by R minus 1. Now apply first law to the closed system for processes 2 to 3. Now we will apply first law to the closed system processes 2 to 3 and in the process 3 to 1 to show that Qin is equals to Cp T3 minus T2 and Qout is equals to Cv into T3 minus T1. So the cycle thermal efficiency is given by, now we will write the cycle thermal efficiency. Is equals to 1 minus Qout divided by Qin. Put the values 1 minus Cv T3 minus T1 divided by Cp T3 minus T2. That is equals to 1 over 1 minus K T1 divided by T2 into T3 divided by T1 minus 1 divided by T3 divided by T2 minus 1. The efficiency now becomes 1 minus 1 over K 1 over R K minus 1 power K minus 1 over R minus 1. Now in the part D of the question, we will calculate the value of back-work ratio and efficiency. Now we will calculate back work ratio and efficiency as R goes to unity. So work done during compression divided by work done during expansion is equals to 1 over K minus 1 over R power K minus 1 into R power K minus 1 over R minus 1. Now we will apply the limit as R goes to 1. So work divided by during expansion. Now it will become 1 over K minus 1 limit. As R approaches 1, 1 over R K minus 1, this term into R K minus 1 divided by R minus 1. This is also minus 1, this is minus 1. Closing the brackets, this will become equal to K minus 1 into limit R power K minus 1 divided by R power K minus 1 over R K minus 1, which will then become equals to K minus 1 into limit R approaches to 1, K minus 1 R power K minus 2 divided by K R K minus 1 minus K minus 1 into R K minus 2. Now we will get 1 over K minus 1 into K minus 1 divided by K minus K plus 1. This will become equals to K minus 1 divided by 1, which is equals to 1. So cycle thermal efficiency will become, this is the back work ratio. Now we will put for thermal efficiency the same limit, 1 over K R K minus 1 into R K minus 1 minus 1 divided by K minus 1. Sorry, R minus 1. Now apply the limits. R approaches to unity and efficiency. That is 1 over 1 by K into limit R1 just to 1 divided by, that is 1 over 1 minus K into limit R approaches to 1 R power K minus 1 divided by R K minus 1, which is equals to 1 over K limit R approaches to 1 into K R K minus 1 divided by K R minus 1 K R K minus 1. minus k minus 1 into r k minus 2. That is 1 over 1 over k into k divided by k minus k plus 1, which is equals to 1 over k divided by 1 equals to 0. This result shows that there is no compression. It shows that when there is no compression, that is r is equals to 1, there can be no expansion. There will be no expansion and no network, and no network will be done even, will be done even. So this is our answer. Thank you.